through all right? Okay, so I'm going to do this geography markup language tutorial. And I'll give you an outline, first of all, to give you an idea of what I'm going to talk about. So basically, I'll give a nutshell summary of what it is, and then a short historical glimpse of the development of GML from the various versions, from version 1 up to 3.3. A little bit about related standards. GML basically doesn't provide a lot of value just by itself. However, it does provide a lot of value when used with some of the other associated standards. Web services in particular, OGC web services, I will mention quite a few times, so there'll be a little bit of overlap with Carl's talk here this morning. Some spatial data infrastructure examples I'll provide. And this basically, all of these topics are overview and very introductory. Then there will be a little bit more about the details, what's in GML, what kind of objects are there, how presentation and visualization is handled in GML. So examples, for example, of GML visualization. More on the components and objects, the features and geometries, the GML modeling rules, and GML application schemas. So this is where you develop your own vocabularies for whatever domain that you're working with. And finally, a little more details on related tools and technologies. Okay, and so a little more details in the subsequent topics. So we'll start off very introductory. Okay, so what is it? Basically, it's a set of XML technologies for handling geographic information on the web. It's an international standard for geospatial data on the web, endorsed by many organizations around the world, always growing, over 500 right now. It's primarily to encode information content, as opposed to visualization. Typically, a separate visualization language or mechanism is relied upon to visualize geographic information. Now, one of the main purposes of GML is to enable transactional data exchange across different databases, so heterogeneous data stores. Now, these data stores could be file systems, but typically databases like relational databases or XML databases. And typically, OGC web services like feature service, coverage service, map service, processing service will be used to facilitate this transactional data exchange. It supports features, coverages, which is considered a special kind of feature, imagery in some applications, and sensor data, observations, that is, and provides a foundation to build application vocabulary. So in a particular domain like urban planning, you can build up some city models. You can hear me better if I was stooping down. I'll try and stay close to the microphone.
Well, you can use your wireless microphone over there.
Or you can hold this one? Okay. No, this should go. Okay, so for urban planning, city modeling, topography, navigation, land, sea, and air, we've seen all three of these applications as in the form of GML application schema, geoscience, and others. Certain domains. Okay. Now, to give you a historical glimpse, basically, it's It's an adopted standard at the Open Geospatial Consortium. And it started with GML 1.0 back in April of 2000. At that time, GML had 3 different representations: RDF, DTD, and XML schema. It turned out that after trials and tribulations, it was XML schema that was the winning representation. So all the following versions of GML ended up being produced, or at least defined, in XML schema. Thank you. Okay. So, GML 2, February 2001. GML 2.1 in 2002. GML 3 in 2003. It looked like there was some very good progress there. A new version every year or so in the OGC. GML 3.1 in 2004. 3.2, GML version 3.2 was a joint ISO standard and named ISO 19136. This was an important benchmark for the development of GML. And it took a few more years, as you see, to get to that, to get to the current GML 3.2 version. Now, GML 3.3 has also been developed, but these are extensions to GML 3.2. So GML 3.3 exists only with GML 3.2. Basically, GML 3.3 imports GML 3.2 and must use GML 3.2. Okay, so it doesn't, not like other versions, previous versions, often a new version would deprecate the previous version, but in this case of GML 3.3, it coexists with GML 3.2. And so this was a result of the OGC policy, slight policy change, and probably one of the first successful implementations of this policy, if I'm not mistaken. Now, from GML version 3.0 and on, it's ensured to derive from the ISO conceptual models in GML. And it wasn't until about GML 3.2 that maturity peaked, so that most of the concepts in GML are based on ISO. Not completely 100% of them, but most of them. Okay. So GML is standards-based. It builds on other standards, and many of them are XML and W3C standards. So XML 1.0, XML schema, XML namespaces, and other XML technologies like XPointer and XPath from W3C, XLink. And so it relies quite heavily on the World Wide Web consortium standards. But also, as I mentioned, the conceptual models come from many of the ISO standards, and you can see a number of them listed here. 19107 that John just talked about, Spatial, 19108 temporal, 109 feature log, 111 is important reference systems, 123 is the coverage conceptual models, 148 linear referencing, and so on. Many of the ISO 19100 suite of standards have been implemented in GML. Okay, now other standards have built on GML as well. The idea is that you do build applications on GML. Now, the Web Feature Service is probably the best or most well-known OGC standard that has a strong dependency on GML. Most of the versions of WFS are required to serve up GML features. The Feature Portrayal Service, in turn, also will visualize GML features. GML and JPEG 2000. This is basically a mechanism to turn a JPEG 2000 image into a geo image, and it's an OGC standard. City GML, one of the celebrated GML application schemas for city modeling. Observations and measurements, another application schema of GML. Aeronautical navigation, AIXM, otherwise known as AXM. This is for navigation and flight planning. WIXM, this is related to AXM and encodes weather events and uses observations and measurement quite heavily. CSML, so climate science markup language. GeoSciML. And others. There's many others. DIGS, OLS. The list goes on and on. So there are several standards that have built on GML since I guess it was probably in the early 2000s that some of these were created. Okay. Now there is an analogy between GML and HTML that I like to show. Basically, the HTML analogy is you have a web client, a web service, a database behind this web service, and typically the web client, the browser, will make a request, an HTTP request to a web service, data is supplied from the database, and HTML is returned to the browser, to the web client. Often, the web service will link or hyperlink to another web service because the data store doesn't have all of the data locally, and so another web service backed by database 2 will provide and return the corresponding HTML that's linked to. Okay, so this is the typical scenario when you're browsing on the web and getting back web pages. But the scenario for GML is not that different. Basically, you change the web service out for a web feature service. It provides that same role. And HTML replaced with GML. And you get basically this analogy. So a web client requests GML from a web feature service, which provides an interface into a database, which the client needs to know nothing about that database. Okay, now also the feature portrayal service can act as a web client. And in this case, feature portrayal service can get the GML data from a web feature service and then provide that to another web client. And typically, it'll style that GML into SVG or KML or some other imagery format. I listed 2 vector ones there. Okay, so it operates over the web. It's designed to operate over the web very much like HTML web pages. However, the content is different. It encodes geospatial information. Okay, the role of the web feature service. I'll go into a few more details here. Basically, is to request and serve GML features over the web. It supports spatial and temporal filters, so you can request roads and buildings by a bounding box or within some containing polygon, or even by time, so in some temporal period. So, if you have a browser client, you can request through a WFS interface and get data from a database behind it. So, in this case, relational or XML is what I'm showing behind the WFS interface. And together, those taken together, that's what we commonly refer to as the WFS, with the database behind it. Now, WFS query is sent from the client to this web feature service interface over HTTP typically, and GET, POST, or SOAP are often supported by WFS implementations. And what gets returned is typically GML in the response. So features come back encoded as GML. Okay, we'll see some examples of this later. Now that is the read-only role of the WFS, but also transactions are possible with web feature service as well. So to make a transactional update, the difference here is the browser or client makes a request, and in this case, GML is in the request. And so an update, a new feature is passed to the WFS interface, and then the response is typically a fail or success and a list of the IDs that have been updated or inserted. So the new features have gone into the database. Okay, typically transactional update will be done on per feature basis. Sometimes a number of features of the same feature type, but typically not too many. So it's transactional in nature, smaller payloads, smaller data loads going across the wire happen in the update scenario. Okay, now when it comes to GML versions and WFS support, we used to have a specific version of GML was bound to a specific version of WFS. And so version 2 of GML was bound to version 1 of Web Feature Service. You can see in the early 2000s there. Version 1.1 of WFS supported 3.0 and 3.1 of GML. And then by the time we got to version 2.0 of Web Feature Service, it became version agnostic so that it can support any of the versions of GML. But it took some time to do that. Now, it's typical implementations of version of WFS 2 will support GML 3.2, but it is possible to implement earlier. Okay. Now, the role of the feature portrayal service basically is to obtain GML data from a web feature service and then style it, apply a visualization to create a map using some selected symbols. Okay, so if we have a standard browser that has SVG support, so we call this the web viewer recording. The feature portrayal service, it's a kind of web map service, a component web map service, gets its data from web feature services. So these web feature services can be different, have different databases behind them, and the map request is made to the feature portrayal service, and the subsequent feature request is made to the individual web feature services. And this is specified typically in a style layer descriptor document. So what comes back from the WFS is GML, and the style layer descriptor document says how to take a feature and style it. So different roads will be styled one way, and rivers will be styled some other way. And so you get back a map of some kind. In this case, the example is an SVG map, but you can use another styling mechanism and another output. In this case, the output can be KML in a different browser, Google Earth browser or something, but also other imagery formats are just as easily supported, like JPEG, PNG, and different kinds of browsers. But that's typically the role that the feature portrayal service plays. It takes GML, styles it to an imagery format. Okay. Now, GML and web services often play a role in a spatial data infrastructure. Here's a simple one where there's a number of databases. In this example, we've got a hydrographic database, as well as some other data that's available. So shipping lanes, harbor facilities, and all of these basically are linked or associated through the web. So land data, aeronautical data, other hazards to navigation. So all of these here, the idea is that GML is used as a transfer format or transfer encoding between these different databases. These databases, of course, are autonomous. They can be regulated on their own schedules by different organizations and use different technology. And it's the web feature service that is providing the open interface between all of these things. And GML is the encoding. So web services like processing service, map service, and data distribution service, web feature service, can provide the raw GML or style formatted GML, like KML, SVG, to other clients and portals. Okay, and so there's an example of GML in action, basically providing the transfer and code to make this spatial data infrastructure possible with OGC, some of the OGC services. In the end, we have a network of managed web services over multiple databases and application domains, and also different geographic regions. Okay, some examples of SDIs. There are many. I'm only going to provide a few examples here. Transport Canada, many years ago, started a pilot spatial data infrastructure. We used a dynamic traffic model to provide basically a color-coded map of traffic congestion around the Toronto area. And there were several different databases that were feeding information into this spatial data infrastructure. Now, there were a couple of different visualizations. One is KML, one is SVG. And in this diagram here, we had different the different databases shown. So one at University of Toronto, these ones were in other cities, and the authorities for these databases were at different levels. So a municipal authority here, provincial authorities here, and so there are different kinds of objects that are needed to display these traffic congestion maps. We needed some static data like the roads and the sensor data that's provided some of the speeds and occupancy information about the traffic situation, and the collection of sensor data together with the building of traffic model are all in different databases. In the end, the user gets a map of the color-coded traffic congestion. So this is very typical sort of architecture where GML is used and distributed from one web feature service to another, so that the end user ends up getting some stylized, processed visualization, in this case, of the raw data. Okay, another example is using City GML in the Berlin City SDI. This is an example with a central database, so not many distributed databases. And so the architecture in this case is different. There are several web services, but one main 3D geodatabase. So there's different architectures, of course, that you can have for a spatial data structure. Several heterogeneous databases or a central repository. But the result in this case, for urban planning and city modeling, City GML was more appropriate for the data transfer format. And so we have City GML interface here, in front of a CAD system, other geo-enabled applications that are processing City GML, and visualization of City GML to KML here. Okay, so this is another example of GML supporting an SDI for its transfer encoding. Now, other city In this case, it's more examples from Germany, where urban planning, mobile network planning, 3D navigation, disaster management, training simulators, noise pollution mapping. All of these are applications of a city spatial data infrastructure. Now, when you have a spatial data infrastructure like this, so a number of different data resources, you can ask questions and perform analysis where you can get answers that require information from a number of different resources. In this case, of urban planning, you can ask questions like, from which windows, rooms, and buildings do I have visual coverage in a certain place? Okay? In the mobile network planning, what is the best position for a new transmitter station, such that the propagation of a radio signal is optimal? Okay, when you have access to various different data sources, and the interoperability is there so that you can process information from many different data sources, you can ask these questions. Okay. Now, I'm going to give a little bit of a technology summary here for GML. GML uses these various XML technologies to enable some of these processes. So there's technology encoding for data modeling, XSD, XML schema definition. DTDs in RDF were used. XML schema seems to have won out mostly because of the tool support in XML schema compared to, say, DTDs and RDF at the time. Technology for selecting and pointing, so XPath and XPointer. Technology for transforming, XSLT. Technologies for linking and associating are used, XLink. And also for graphical rendering, VRML, X3D, or other examples that I haven't given already. And now all of these technologies make up the suite of XML technologies that are used by GML. And it's successful because there are tools that back up all of these technologies. Okay, so the question is, why is GML based on XML schema? It did, in the beginning, start off as RDF and also DTD, basically because of the tool support. So there are standard tools that can be used. You don't have to go and create your own custom tools to process and validate data. It was easy to integrate different kinds of data using XML. It's self-documenting. You name your own tags, and also people can read and understand the data. So applications of XML. It began with the description of documents, but any kind of data structure can be described. And so it expanded to applications like geography, architectural engineering, mining and exploration, petroleum, math analysis, there's markup languages for finance, graphics, and so on, hydrography, chemistry, land, and sensors. Okay, so typical usage of XML. Now, it's either mixed content in a single document, so this is the inline approach, where you can have different information objects representing, say, land titles, parcel geometry, utility connections, and taxes, all in the same document. Or you can separate and link different documents using X-links. So you have that option and flexibility to arrange the data in different ways using XML. And GML makes a very, very strong use of that flexibility. So, tools, Xerxes, Saxon, these are XML parsing tools that are easily available. They can be utilized to do all kinds of common tasks. The typical ones for parsers are, if if you have some satellite data that you serialize to XML, then that XML data can be put through an XML parser, which is often can be schema aware. So the schema behind that data can be read, and then objects, programming language objects like Java objects, for example, can be created, and you can transform that data that you collected in many different formats so that other applications can use them. Okay. Other tools, basically, once your data is in XML, you've got a whole world of common tools that can be utilized. So give Xerxes some examples for parsing and validating. But there's also XPath tools, XPath processors that can be used, XQuery tools, tools for transforming XML data, XSLT processors, that was excellent, resulting excellence, data visualization tools, and even things like specification of web services, the WSDL. All right. Now, GML focuses on information content. So, for example, describing buildings, roads, water bodies, and other mechanisms are used for the visualization. Okay, so SLD, SVG, KML, for example, can be used to read that information content. And from the same information content, you can have many different styles. So you don't focus on the presentation of the styles, because there's infinitely many ways you can style the information content. So GML just focuses on the information content. So that same data there can be represented in all these different ways, with blue roads, or red roads, yellow buildings, whatever the scenario is most appropriate for. Okay, so we have examples of GML rendered as KML by Google Earth, GML rendered by Land Explorer, in this case CityGML. Also many CityGML visualizations in Google Earth. Okay. Now when I go into many of the different components and objects of GML, one of the main ones is features. Features describe the real world as objects of countries, continents, provinces, roads, moving vehicles, bridges, dams, buildings. Now coverages are a special kind of feature, and it's a feature where basically it maps a geographic region to a distribution of values. So in this case, we've got heat maps, storefronts, digital elevation models are examples. Now features, basically GML provides a framework to construct objects, which we call geographic features. They model the real world. There aren't many concrete objects in GML, they're mostly abstract. So the idea is that you have to develop your own application schema to develop your own versions of features. In other words, a road isn't the same for everybody. We can provide just the abstract model to build a road, but different communities have different definitions of a road. Okay. In this case, we've got different kinds of features, coverage, observations, and features that are built from specific application communities. Now in CityGML, we've got a feature model, and of course it derives ultimately from the abstract feature in GML. CityGML has been written in version 3.1 of GML and earlier. So it doesn't have the GML 3.2 abstract feature in there. However, it works the same way. The city object is the fundamental abstract object in GML. And then you've got many different kinds of features in GML. So buildings, transportation objects, reliefs, water bodies, vegetations. And all of these have some kind of geometry property. Okay. So let me give a few examples here. In GML, we have different levels of detail. Now that means basically that there are different properties on features, and these different properties show geometry at different scales. The levels of detail basically go from one resolution to a higher resolution, or to the opposite in scale. Starting at level of detail 0, typically you have just footprints of buildings. So it's a 2.5D landscape model. Level of detail 1 extrudes those footprints so that you have heights. So you have actual 3D coordinates for your buildings. And typically includes just prismatic structures without any roof structures. It's level of detail 2 where you get detailed roof structures, but they're still fairly simple ones. And then level of detail 3, you get textures included, so you can also provide a description of some detailed architectural models. It's level of detail 4 when you provide enough information so that you can describe the inside of buildings, the rooms, the windows, doorways, and things like this. So we call it the walkable architectural models. Okay, so here's some concrete GML features. Basically, a building can be broken down into building parts in general. Some of these are interiors of a building, like a room, openings in rooms, so doorways and windows, the boundary surfaces of buildings, so the roof structure and wall surfaces. And so we have some more concrete features at this level. Now typically we see the LOD1 type features are yellow here. LOD4, you get the room level of detail. LOD2, we've got roof structures and wall surfaces, and LOD3 is there in blue, so the windows and door openings. Okay, so at LOD4, this is where you can get the description of the ground, the floor, the rooms, interior walls, and so on. Okay. Coverages. Coverages, again, these are a special kind of feature. Basically, it's a distribution of a quantity over a geographic region. So we can think of a coverage as a function from a domain to a range. The domain is the geographic region, so basically the geometry, and the range are the values that are taken on the geometry. Okay, so here's some examples. You tend to classify coverages by different domain geometry. So we have discrete point sets which form the domain, and we call them point coverages, so grids and unordered point coverages are in this category. Segmented curves, so if you chop up a curve into different segments and they carry different values, you'll have a segmented curve coverage in that case. And surface tessellations, you triangulate or just subdivide surfaces into different polygons. Each polygon carries a value, say with a population, then you'll have a population distribution. And so that's another example of coverage. Coverages have different encodings. The binary file encoding is one where all the values that correspond to the geometry are kept outside of the GML encoding. So it's an external binary file that carries these values. The GML encoding will tell you how to map the different pieces of the geometry to those values. So it describes mapping rules from the geometry to these values. Okay, so examples of that are remotely sensed images, so the pixels, the binary encoding of an image. Basically carries, it could be things like color, RGB for each pixel, and those values have some meaning. Either it's color or it could be other things like heat maps or digital elevation models, photo logs, and so on. Now, one example of that external binary encoding is GML in JPEG 2000. In this case, the binary values are external to the GML file, but they're all packaged in the same envelope, the JPEG 2000 package. In other words, the JPX file. So it is an example of the binary encoding of color, but it's all retained in the same binary file, this JPX package. Okay, GML and JPEG 2000. Well, basically, it was an extension of JPEG 2000, where JPEG 2000 offers flexible imagery formats with waves of compression, and by including some XML boxes in with the JPEG 2000 code streams, it was possible to make images, geographic images, so that you can geo-rectify some of the digitized features that you can identify in the image. So it's also known as GeoTIFF on steroids because the JPEG 2000 capabilities are quite good, and the geo-rectification using GML is better than most. It also includes a description of the features inside the image. So now features are typically extracted from the image. The image is taken first, and then features are identified from it, and then described in GML. You can integrate things like observations, so sensor data and metadata about the image, and also store it in the XML box part of the JPEG 2000 file. Okay, other components and objects. Observations, another kind of feature. These are features that capture the act of observing. So typically observations are made by mechanical sensors. In this case, we have an example on a highway. We've got road features, and other sensors themselves are maybe represented as features. But the data that they record are what we call observations. So if we have traffic sensors, the observations can all be sent as observations recorded in GML to a feature service or a sensor observation service. We'll just generalize that to a GML data server. And in real time, you can process these sensor data readings and generate, say, a real-time traffic model from that. Okay. More kinds of GML objects, geometry objects. So John has talked quite a bit about these. Basically points, lines, polygons, how they get represented in spatially, so spatially referenced. This is what's implemented in GML. Most of the data sets carry linear geometries, but some carry non-linear geometries. Topology can also be described This is new in, this was new in version 3.0, that's where it was introduced. And it basically implements the ISO 19107 model for geometry ecology. Okay. Now, some of the geometry classes that have been around since GML are the linear and aggregations geometry. Points, line strings, polygons, and then aggregations of these like multi-point, multi-line string, multi-polygons, and then multi-geometry. So these have been around since GML2. Curves were introduced in GML3, but typically linear interpolations are what you commonly see. In this case, we have a GML line string. This is one of the examples of an implementation of ISO 19107. However, it's not one of the objects in ISO 19107. It's actually a sort of a compressed encoding of a GM curve. Now, this line string object existed before in GML version 2, before it was based on ISO 19107. So it has history before that, but it does implement 19107, and that mapping or implementation is described in the GML spec. So in this case, we have different kinds of interpolations for curves. This example is linear. Basically, what GML encodes are the control points, okay? And the fact that you're using a curve called line string means that you're using linear interpolation. When you use a GML curve encoding, you're very explicit about what the interpolation type is. But line string happens to be linear. Now, control points, they can be a distinguished point with its own identifier and referred to, or it can be a point where the different coordinates are encoded for it, but not identified. So there are two different ways to do that in encoding control points for a line or a curve. And typically, where you're going to join two curves, you would encode one of them as using coordinates, and then you would refer from another curve that joins to it to the idea, the idea of the endpoint, just so that you don't duplicate coordinates for different control points that are shared. Okay. Now we've got curves that can have different kinds of interpolation between control points. Here's an example where we have a GML arc and then some line segments followed by a GML Bezier curve. So it can be composed of segments. In this case, a curve carries an identifier, but the segments do not. So you do not have separate identifiers for the sub-segments of this curve. You can, however, create a composite curve where it itself is a curve, but its components are also identified so that you can share different components of a composite curve. You can share the middle part, for example, with a polygon and not have to redefine it. It can just reference by the ID of the middle component curve. Okay, so that's what distinguishes a curve from a composite curve. You can have different interpolations amongst the different segments, but composite curve, each component is a full curve in itself and therefore identifiable. Okay, surfaces in GML. Polygons can be encoded. They have at most one exterior boundary and one or more or zero or more interior boundaries for a represent basically the holes inside the polygon. Here's an example encoding of one. So the GML polygon has some properties here. The exterior boundary is encapsulated by this exterior tag, and then a boundary ring is encoded, and 0 or interior can follow that. In the case of city GML, we've got feature semantics are associated to geometries. In fact, this is always the case with GML. And that is distinguished from other formats like KML, S3D, VRML, which focus only on the geometry and encode only the geometry. So that from all the, from an encoding which is like a bag of polygons and vertices, you can't really tell what's a wall, what's a roof, and so on. Okay. The interior model of city GML building typically is a description of rooms and how those rooms are attached to each other. So in this case, we've got a back room, a living room, a hallway, and we've got doors, entrance doors, or passageways without a door or with a door. And from this geometry model and the way the geometry is shared between them, you can deduce some topology from it, and you're able to use the connectedness of the geometry, the sharing of the geometry, to extract an escape route, so some topological information. So an escape route, maybe the best escape route from a building if you start in a certain room. Okay, GML topology is implemented in GML. It basically was introduced in version 3 based on ISO 107 and provides encodings for all of the, or most of the topology primitives in ISO 107. Nodes, edges, faces, solids. It does include boundary and boundary relationships that John talked about earlier on, including orientation of edges and faces. It includes encodings for a topology complex and a very simplified topology expression called the topo curve. But it doesn't have encoding for the full topology expression. Okay. The boundary and co-boundary relationships include orientation. So directed edges, in other words, can emanate out from a node, and a polygon or a face can have an oriented sequence of directed edges to form its boundary. The geometric realization of any topological element is possible to encode in GML. Basically, there's two ways to associate topology to geometry. You can have geometry embedded in the topology, or it can be shared. Here's an example. We have a GML topology model where we have separate models. A topology model that consists of the node, edge, and face descriptions, and a separate geometry property that holds the geometry, so points, curves, and surfaces that realize those topology primitives. Or you can encode it this way, where you have a topology model, and the geometry is embedded inside of it, so that each node references a point, the edges get realized by a curve, and the faces get realized by surfaces, like so. Okay. However, in order to get to those geometries, you have to go through a single property in this case. Okay, other types of GML objects. We've got coordinate referencing objects. This gives
basically the spatial context for where your object is relative to an Earth model. We've got, it used to be that default styles were in GML. They've been since deprecated, and in GML 3.2 they're strictly informative, not normative anymore. And that's because the separated of information content and visualization. So that has pretty much succeeded in that you have a single information content description, but many different kinds, many different styles possible of that. And so default styles basically weren't well utilized in GML and deprecated. Okay, dynamic features. So these are features that move in time. So things like moving particles, descriptions of moving storm fronts, and so on. Time objects themselves that support these dynamic features, so time instants, time periods. The GML temporal model comes from ISO 19108 and basically includes a description of a time instance and also time periods that support dynamic features. So the time instance, they can be identified, they can be given a reference frame, very much like a point, where the reference frame is typically a Gregorian calendar, UTC standard, but it can also be things like ecological eras or other reference frames. Okay. Dynamic features typically keep a history of time slices. So it's a varying time parameter, so you get a snapshot of each time slice that made up a dynamic feature. This is a discrete dynamic feature. You can define your own timescales and calendars, just like you can define your own spatial reference systems in GML. Moving object status was an example of a concrete dynamic feature that had its own properties that can describe a generic object. So things like motion of vehicles, flood boundaries, or the changing size and shape of fire or earthquake impact areas. Okay, now GML also has a model that it follows, objects and properties, and the objects are defined in the core schemas. Application schemas are based on these core schema objects, so GML point, line string, coverage, etc. The application schema objects corresponding to those basically will be features like roads, rivers, or people, and their properties will have values which are often typed by some of these GML core objects. Okay. So application objects have to be defined by user bodies or communities of users that agree on certain vocabulary that describe the real world. Now, in order to derive an application object from core objects, this is how it looks in a pseudo-UML diagram. We can have a road defining one application domain that derives off of the abstract GML feature. Now, a highway can be specialization or an extension of a road as defined by another domain and would typically be in some different namespace. So each application domain has to have its own different namespace or use multiple namespaces. Okay. Now, by looking at the source type at any application schema, you can always tell what kind of object, what kind of GML object it is. You can tell if like a road is a feature type, but there's other kinds of objects like metadata objects, geometry objects, and these are all strongly typed so that software can go through and find out what are all the objects in some application data files. Okay. Now here is a UML class diagram in comparison with a GML description of a feature. So we've got basically the road feature. There's a class that subtypes off of the abstract feature. In the GML encoding, you would have an element and element declaration and content model, or complex type. And these correspond very well to the UML classes. So each UML class corresponds to an element declaration and content model. And so the mapping is quite clear. You can create a mapping between UML and GML. Associations correspond to properties of GML as well as attributes. Typically operations, they can turn out to be values of properties or just not expressed at all in GML. Okay, so each of the GML objects, its child element is a property, and these properties can represent associations between classes. So typically we have an object, a value, and in the case of a simple property, the value might be a string, an integer, a boolean, or something like this. If the object is more complex, it's another object, the value is another object, then it's a complex property. So metadata, for example, geometry, or other features would constitute complex property values. Okay, in general, we have basically an object, property, object rule. And this is the model that GML follows. It maps very well to the UML class association class model, or even the RDF object property value model. Okay, so features. Here's an example of a feature. Take a person to be the feature type. And you can describe a person by properties, basically name, description, age, height, weight. And so all of these properties are the immediate child elements of the feature. We can map GML features to relational databases quite easily. Typically the feature type maps to a table. So a bridge feature will map to a bridge table. The properties would map to the column headings, and the values would be the rows under the column headings. So it's fairly straightforward mapping. Okay. Here's an example where we have an association between a bridge and a river. In a linear diagram, we would have the bridge is an entity in a relationship to a river entity. This is very much like the object property object rule in GML, or the class association class in UML. Now, in this case, we would represent the bridge as a GML object, the crosses relationship as a property, and the river object is the value. And so each object maps to, or in this case feature, maps to a table. And the association can also be captured by a table. And so in a relational database, we would have 3 different tables here that have keys and pointers to each other to represent this object property object model in GML. Okay, more on properties and relationships. Basically, the value of a property can be either inline or remote. And here's an example of an inline association. We've got a road intersecting another road, and we've got the road element embedded inside the first road element in line. Or we can do the same, we can code the same thing but using remote properties. In other words, the intersects property that we had in the previous example, which is this element here, rather than having a child object, it can use an excellent href that can be resolved. And so you have two different road elements that link to each other. Okay, now GML application schemas. Basically, in order to use GML, you've got to create an application schema to represent your application domain. And this is where you define your features so that you can write your data instances against. So the GML application schema is written in XML schema, plus it imports GML and uses the GML model and rules. In the instance, you describe the feature types. Okay. Here's an example of an application schema that's built up on top of GML objects, which the GML objects describe your common geographic and geometric constructs. The application schemas are your domain vocabulary, so if you describe geotechnical constructs, monitoring constructs, geo-environmental constructs, and it's the GML geometries and feature model that gets imported by these application schemas. Then GML in turn, it uses W3C constructs like numbers, strings, and things like excellent. So there it is in a tier diagram. An example of this is for hydrographic application schema called S57. We've got the application schema objects up on the top in blue. So the various objects, attributes, and things like that. They import GML objects from the GML namespace, which in turn imports some XML or excellent objects from the XML, some of the XML namespaces. Okay. Now, when creating GML application schemas, there are some rules and best practices that to follow, and these have been developed over years of creating application schemas by different communities. And basically, properties of features, other than or even other objects in GML, are represented by elements and not attributes. So you would not encode a new geometry like this ellipse. You would not represent semi-minor and semi-major axes using attributes, mainly because GML-aware software would not interpret these as properties, wouldn't understand how to process this. And there are really only a few attributes, XML attributes used in GML, such as the identifiers, the spatial reference system names, and excellent href. So attributes are used as supportive constructs only, typically not used for defining characteristics of an object or a feature in GML. The role of attributes here is an example. Basically, the corresponding valid GML encoding could look something like this. For an ellipse, you would have sub-elements or child elements of the ellipse, and they would describe your semi-minor, semi-major axes, possibly the center. So we've got rules rules about, or conventions about local property names. Basically, property names should be descriptive and if appropriate, describe the relationship between the value and the parent object. So, for example, if you have a building, a property with the name of point property isn't very descriptive and doesn't expose the relationship between the building and the point. What's recommended is to name your property something more specific, like center or northwest corner, so you get an idea of what that point represents, in relationship to that building. And so basically it should have some semantic meaning. Okay, complex properties. So take this example. It's not recommended that if you have a feature and a property, the value should be another object of this property rather than a number of elements. If you encode it this way, GML-aware software will not recognize this as an object and would have to treat it like generic XML. So rather than that, this is the encoding that's recommended. So descriptive property like a forwarding address, and then an object address that can be identified and reused by other features. Okay. For other complex type definitions, taking the example of the address again, you can define it something like this. What you see here on the left, or like this over on the right. What's the best practice recommendation is that you name your complex types so that you promote sharing of types. If you name it like this, then you can reuse it later on in another application schema, extend it, or restrict it. But if you don't name it, then you basically eliminated the possibility of doing that. Okay. So in general, complex types are intended to be reused. You name them so that they can be referred to. Let's see. In creating application schemas, if you don't find a geometry type available, you can create your own. So the example is the ellipse here. Now, when doing that, basically you should derive from the most appropriate GML type. Not something generic like abstract geometry, but derive it from a curve and use the abstract curve type. So if the thing you're creating is a curve, then you derive from the most, the closest matching GML type. Okay, for some topological best practices, if you have two different road networks, you have some choices on how to code them, but your GML topology encoding should distinguish one from the other, and there is a way to do that. In GML 3.2, you can distinguish two road networks such that they really do represent different things in the real world. In this case, you can have two loops that either enclose a hole in the surface or do not. And depending on your GML encoding, you'll get one or the other. I'll give an example of this. Basically, we have the first example on the left and the other example on the right. By encoding the directed edges that emanate from a node in clockwise order. So I've got the color coding going clockwise. Basically, the directed edges in the list on the left here are going black, blue, green, red. And if you follow this clockwise here, black, blue, green, red, that corresponds to this picture here. But if you change the order to black, red, blue, green, so black, red, blue and green going in clockwise order. You have something very different. And they correspond to basically these two pictures here. So you really do need to keep track of the order of the directed edges emanating out of the node in order to distinguish those two cases. Now, related technologies and tools. This is one of the last sections that I'm going to talk about here in this GML tutorial. So, GML schema parsers, Spatial web services, and registries, schema registries, and word reference system registries. So these are related tools, services, and technologies that are often used with GML. In this case, a schema parser can take a GML application schema and detect all of the different kinds of types that you can encounter. So it can determine which things are features, which things are properties, and what values those properties have, whether they're geometric values, metadata values, associations to other features. So other features can be values. Sometimes the value of a property can be a coverage, which is another feature. So GML-aware software or schema parsers can go through and detect these things because of the strong typing in GML. Okay? And they're meant to parse and interpret the content of application schemas. That way you can build application objects that can be used to further process the data in the programming language. Okay, the web processing service. Basically the idea is that it exposes a set of signatures. Okay? What are the inputs, outputs of a process? So what it'll return if you give it a certain inputs. And it can be GML can be used in request and response in some web processing services. Ones that process GML, particularly GML geometry. Examples of that have been seen where geometry is sometimes clipped to a certain bounding box, and so a processing service will go through and do the clipping process. Web coverage service. Again, you can make a get data request to it. It will return a GML coverage in encoding. And so GML can be used in both the request and response in this case. Schema management. So many schemas are produced with many versions, and managing schemas can be quite a task, especially GML application schemas. So an application schema registry has been developed in the past. So a repository containing the actual schemas, and the registry objects are individual elements that can be discovered or managed over a certain life cycle. UML models can be used to generate application schemas. There are examples of UML to GML conversion tools out there, shape change and Hollow World, Full Moon, I believe. And then application schemas can be developed and managed in such an application schema registry. Okay, so this is a completely automated process starting with UML models, and then you end up managing the resulting application schemas in a registry tool. Okay. Recorded reference systems can also be managed. So a web feature service request can be made to a web feature service so that you get your features back in a certain recorded reference system. And so recorded reference transformations have to be applied and such transformations and port of reference systems themselves are managed in the life cycle is audited in registries. There's an example of the EPSG port of reference system database that's managed online, and you can get a GML description for every one of those port of reference systems and the corresponding transformations between port of reference systems. Okay. All right, so that's the end of this GML tutorial. So